Okay, let's talk a little bit about the binomial setting. Again, we talked a little bit about it in a previous video. I'm going to walk through it one more time, do a couple examples, just so we have an additional practice to kind of look at. So again, binomial settings. Here's what we know about a binomial setting. This is going to be the formula. But when I look at a binomial setting, I need to ask myself 3 questions. So let's take a look here. Assume that 18% of people are left-handed. If we select 9 people at random, find the following probability. So if we're going to think about this as a binomial setting, here's the 4 questions you have to ask. The first is it binary? Do we have a success? Do we have a failure? So in this case, the answer is yes, we do, because we would say left-handed is a success. We would say right-handed is a failure. So the first question is we had to ask ourselves that. The next one is independent. In other words, let me ask you, does it matter if I randomly select a person? Does their handedness have any bearing on the next person's handedness? Just in general, if I was randomly selecting a person out of a population, would me being right-handed have any bearing on what the next person is? The answer is no, and so the reason it's independent is because one person's handedness doesn't influence handedness, doesn't influence another, doesn't impact others. Okay. The next thing that we have to ask is it a fixed number of trials at the beginning? From the very beginning, do we know that we are doing it a fixed number of times? Well, this one says 9. So in this case, it's yes, Rn is 9. And the S is that the success probability stays the same. And in this case, we can say yes, according to this problem, the probability is 18%. So that's a binomial setting. You have to ask yourself that question. So like looking here, about 8% of males are colorblind. A researcher needs some colorblind subjects for an experiment and begins checking potential subjects. And in this case, if I said how many colorblind subjects, let's say we're going to select this one. Let's say that we were going to select 50 subjects. Okay, let's say in this case, we're going to select 50 subjects. So in this case, if we read this initially, it doesn't have a fixed number of trials. It does have a probability of success remaining the same. You would assume independence because one person being colorblind should not have any impact on anyone else. That's the independence. The binary is that they either are colorblind or they're not. The one that we're missing was the number of successes. So in this case, I would need the successes. And if we go through here, you see the successes are provided. So that's our binomial. And what the binomial is a formula. It's basically this. It looks complicated, but here's what the formula is, kind of in its simplest terms. We want to figure out how many ways to get a certain number of successes. So that's our K of successes. So again, let's put it in its simplest terms. Let's say we're flipping a coin. We're going to flip a coin. And we're going to flip a coin twice. And we're going to say, what is the probability of getting exactly 1 head? So if you remember back to when we did this before, we made ourselves a tree diagram. And what we said is when we flip the coin the first time, we get a heads, we get a tails. It's a 50% probability. It's a 50% probability. We get a heads, we get a tails. It's a 50% probability. It's a 50% probability. We get a heads, we get a tails. It's a 50% probability. It's a 50% probability. It's binary because you have heads or tails. It's independent because one flip doesn't impact another. There's a fixed number of trials. We're doing it twice. And probability of success stays the same at 0.5. Well, in this case, what we'd want to do is we want to look at these 2 probability rolls. And the way it would be is we would do 0.5 times 0.5. So that would tell us the chances of getting heads tails is 0.25. This one would be 0.5 times 0.5. This would also be 0.25. This is getting heads tails. This is getting tails heads. Both of these are exact. They're mutually exclusive. So what that says is I can add them together. So it tells me there's a 50% chance. Well, this binomial setting allows me to get there a little quicker. What it tells me I can do is, okay, with a 2-1, you can do a tree and probably get it. But imagine I was saying flip this 200 times. what it says is, I want to have N 2 trials. I want to have exactly one success. My probability of success, P, is 0.5. I want that to happen one time. My probability of failure, 1 minus P, so 1 minus 0.5. I want that to happen one time. So this tells me the number of ways I can do it. So it's going to tell me how many ways in a tree. And what's going to happen is, the really nice thing is, once you do this, I'm going to want you to pick up your calculator. When you pick up your calculator, second plus 7, 1, 2. We're going to go to second. We're going to go to vars. We're going to arrow down until we get to A and B, A and B. A is binomial PDF, B is binomial CDF. Binomial PDF is an exact. That's being exactly one success. That's what we want. So now it's saying the number of trials, 2 trials. The probability of success is 0.5, and we want exactly 1. When we hit enter, it gives me that same 0.5. So it gives me that same 0.5. So this is equal to, in the calculator, we do binomial PDF, and it's going to be 2, 0.5, and 1. So this is my number of trials. This is my success probability, and this is exactly 1. And when I do that in the calculator, I get my 0.5. Now, again, from this tree diagram, you could have probably done it, but again, imagine I said this. Flip a coin 50 times. What's the probability of getting exactly 25 heads? Well, in that case, this tree diagram would blow up really, really quickly. I mean, it would get really huge. Whereas what can happen is, we do this in the calculator, we do second, we do vars, we go to binomial PDF. We say we're doing it 50 times, probability of success 0.25. 25 is my exact value. And what you're going to find out is the probability of you getting exactly 25 heads is about 11%. So again, that's the shorthand way of doing it. So you don't have to make this massive tree diagram. So that's our binomial setting. And what PDF does, PDF gives you an exact number. CDF gives you that number and below. So let's take a look at a couple examples. So here's my examples. Assume that 18% of the people are left-handed. If we select 9 people at random, find the following probabilities. There are no lefties among the group. That's an exact number. No lefties would be 0. So that would tell me that letter A would be the probability that X is equal to 0. It would say, I have 9 people. I want 0 successes. 18% would be lefties. I want 0. 1 minus 18 and 9 times. So that's going to kind of be my formula. Or in the calculator, since it's an exact, I'm going to do binomial PDF. I'm going to say 9 for my trials. I'm going to say 0.18 for my success probability. And I'm going to say 0. I'm going to say exactly 0. And then what's going to happen is, I'm going to go to my calculator. I'm going to go ahead and do second vars. We'll go to binomial PDF. 9 trials, 18% probability, exactly 0 successes. And it's going to say about 0.1676. So this probability is equal to 0.1676. I want you to take it to 4 decimal points. So what this is saying is that it's not statistically significant. I mean, the probability is 16%. It's not great, but it's not like unlikely to get none when you grab 9 people. Okay. The next one. There is at least 1 lefty among the 9 people. So there's at least 1 lefty. So sometimes this helps. At least 1 lefty out of the 9. If you think about it, here's all the outcomes you can have. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are the outcomes. And it's saying at least 1. At least 1 says, I want all of these people. So it's actually saying, what is the probability that this X is going to be greater than or equal to 1? Okay, now this is going to be where what we need to do is the calculator can't tell me this direction to the right. It can't tell me greater. The calculator can only tell me less. So what I'm going to do is I want to take this guy and I'm going to remove it. And the way you do that is 1 minus the probability that x is less than or equal to 0. So that's how we're going to do that. And that right there is going to be using the calculator. What we're going to do is when we see less than or equal to 0, that is going to be a binomial CDF. CDF tells me number less. And it's the same arguments. So it's 9 trials. It's the probability of success is still 0.18. And this one I want 0 or less. I know that doesn't seem to make more sense, but I want you, because you can't have less than 0, but I'm going to call it that. So 1 minus binomial CDF 9018, 0. So that's going to tell me that probability of greater. So again, what's going to happen is 1 minus second vars binomial CDF, 9 trials, 18% success, 0. And what that's going to tell me is 0.8324. It's going to tell me in this case that the probability that x is greater than or equal to 1 is going to be 0.8324. So the probability, if I were going to grab one, that I have 1, 2, 3, 4, 5, 6, 7, 8, or 9 would be about 83%. But if you think about that, that's kind of the complement. Having 0 is 16.7. Having the rest is 0.8374. So the hard part about this one, I'll be honest with you, is when you read the question and figure out whether it's PDF or CDF. So when I read through these questions, there are exactly 8. The word exactly tells me it's going to be a PDF. More than 4 lefties. More than 4 says I'm going to have to get a range. So I'm on 4, 5, 6, 7, 8, or 9. But remember, in the calculator, it doesn't tell me how to go greater. It only tells me how to go less. So in this case, what I'd want to think about is I'd want to think about this guy as saying more than 4. Is there 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9? More than 4. This is what I want. So what I need to do is I need to figure out this range. So I'm going to do the CDF of 4. And then I'm going to do 1 minus that, take it out, and that will tell me what I have. So today in class, we're going to do that. So hopefully that kind of helps in terms of a little bit of practice. Please use a reflection, ask me questions, and let's hope that this kind of starts to click a little bit for folks. Again, please ask if you have any questions.